We are going to give this a second go. Come to find out that my new recording setup does not favor tape with the heat from the light. That came out rather awkwardly. But today we are going to talk about how to predict products, how to make sure something is charge balanced, and how to balance or use molarity to determine what an initial concentration of something was. Okay. So to start with, I've given you this aluminum hydroxide and this barium sulfate, and we want to know what is going to be produced on the other side. So I'm going to rewrite this so we can kind of look at the charges. So I have, what color do I want? Let's try this. I have Al, there we go, OH3. And one of the tricks that you might have seen is that we can take these subscripts and move them up to the top to predict what our charge is. So for the aluminum, for the hydroxide, I have just this 1 coming up here. And the other thing to keep in mind is that the first species is going to be our cation, and the second species is going to be the anion. So if I look at this here, then that says that I have 3 plus charge, and then hydroxide is going to be a -1 charge because it comes second. So now the reason why this works, let's look at this explicitly. To be charge balanced, so in other words, I'm told that this is neutral. When I don't have anything with a charge listed above it, then that means it's a neutral, either compound, a neutral compound. And so that means that the sum of all these charges has to equal 0. So let's see, let's look. That says that I have a +3 charge on the aluminum, and I have 1 aluminum atom. And I'm going to add that with the next one. I have a -1 charge on the hydroxide ion, and I have 3 of those. So 3 minus 3, well, that is indeed 0. That makes that thing neutral, and the charges I predicted are correct. Let's move on then to barium sulfate. Let's try the same thing there. I have BaSO4. So my cation, that's going to be the positive species. My anion is going to be the negative species. And so I might be tempted to say, okay, there's a 1 subscript inferred for each. So that would make this a +1 and this a -1. And now is where we see the tragedy that is my current stand, and that my periodic table lives in there. So if you can grab a periodic table, you'll notice that barium lives in the second group. So second column in from the left. And that means that this has 2 valence electrons to lose. Well, if it loses 2 valence electrons, that's going to make it a +2 ion. Well, if there's 1 to 1, then that means that this must be a -2 ion. Or the other way you can do that is to memorize them, but it's always nice to be able to pull out a tool and use that to predict things. So now we know the charges on them. Let's just kind of see how they come together on this side. So I am going to I'll just start with aluminum because I have it written first. So I'm going to take this cation and mix it with barium's anion. So we're just going to swap partners, if you will. And that gives me, let's see, Al3 plus and a sulfate ion, SO4 2 minus. So just as I put the charges, or figured out what the charges were rather, from the subscripts, now I can use the charges to figure out how many of each. Now to keep this balanced, let's rewrite this little guy down here. I have a +3 times how many do I need, plus a -2 times how many do I need. And that needs to equal 0. Well, I look at this, well, the way to fill that in is that I have to have 2 of these to get positive 6 and 3 of these. The other way is bringing this over here and this over here. So that means that I have 2 sulfate ions. This is a polyatomic, so now I am going to put my parentheses around there, and I have 3 of those. Let's go ahead and write it neater above. So I have Al2 parentheses for the polyatomic, SO4 3. Sweet. Let's repeat the process, but with barium and our hydroxide. So I know that barium is +2 and hydroxide is -1. So I'm going to pull the 2 down. So I have 2 hydroxides and just 1 barium. So let's write that neater. That means plus BaOH2. Sweet. Now we can balance. One of the first things that I key in on is that, well, let's see, I have 2 aluminums here and only 1 here. So it seems to me that no matter what I do, I'm going to need 2 aluminums. I might end up having to increase that, but we can just start there to see what happens. So now I have 2 aluminums, 2 aluminums. I have 2 times 3 hydroxides. So I have 6 hydroxides, and on this side I only have 2. So that tells me that I have to have 3 in front of here to give me my 6 hydroxides. So now I have 3 bariums and 6 hydroxides. I come over to this side, like, okay, I have just 1 here, so I have to have at least 3 here. So that gives me 3 bariums here, 3 bariums here. I know the hydroxides balance. I know the aluminums balance. What about my sulfates? Well, the 3 coefficient means that I have 3 of this polyatomic, and bada bing, over here I have 3. So I am now balanced. So let's do something with this, shall we? What if I told you that I had 15, I'll do a different color. I did 15 milliliters of 0.3 molar AlOH3, OH3, and I used, I'm not going to tell you, I almost did it again. It's a mistake I made last time. What did I say? I used 30 milliliters, I believe. Yeah, 30 milliliters of BaSO4. And I don't know the concentration of the BaSO4, and that is my goal. So one of the things that I can do, if I'm saying that all of this is reacted, is figure out how many moles of this I have. And one of the things I'd like to do here, just by way of example, is relate this to my barium hydroxide. So one of the questions I could have is, what is the molarity of my barium hydroxide in the end? That's an interesting question. So I can do that. I can say, if this thing completely reacts, I can go from here to the molarity here, or if I'm told that I have enough for all of this to react, then I can go from the moles I have here to the moles that I would have here. Let's do it both ways. So one of the things I want you to concentrate on, or key in on rather, is that whenever you see that you've been given a volume and a molarity, that the first thing that comes to your mind is, well, this is moles per 1,000 milliliters. If I have the volume of it, I can easily take this information and go to moles. Once I have moles and I have a balanced equation, well then I can go to moles of anything that I actually will produce or react, We did the limiting reagent last time, so you want to double check on that, make sure you're comfortable with that, because the other thing I could do is give you a molarity here, and we have to figure out the limiting first. But that's not what we're doing here, so let's start. I have 15 milliliters of AlOH3, not 2, OH3, and, well, this is just a conversion factor. So that says that I have 0.30 moles of AlOH3 per, and instead of writing it in terms of liters, I can just go ahead and write that as 1,000 milliliters of AlOH3. Cool. Do a quick unit check. I look at this. I have milliliters of AlOH3 and milliliters of AlOH3. So now I'm in moles of. And this might seem like a waste of a step, but things are going to start getting more complicated, so it's a really good habit to get yourself in now. Okay, so now my moles of this, and I can use my stoichiometric coefficients to come up with a ratio of anything. So first let's start, well, pointing at the screen. First let's start by looking, we'll just jump right to the BaSO4, and then we'll use the other one, finding the molarity of the BaOH2. Okay, so if I have 2 moles of aluminum hydroxide and 3 moles of BaSO4, barium sulfate, I can relate those with their mole-to-mole ratio, like this. So here is my moles of aluminum hydroxide. I need it to go away. To make something go away, I divide by itself because that just equals 1. It's the same thing that happened here. So I need moles of AlOH3 on the bottom. So those divide and become 1. And let's see what goes there, though. I have 2 moles of AlOH3 to 3 moles of barium sulfate. That's what those coefficients mean. So put my 2 here to 3 moles of BaSO4. Let's double check our units. Now look here, moles of AlOH3 cancels out with moles of AlOH3, and this leaves me, my volumes have already canceled, leaves me with just moles of BaSO4. So my trick with my calculator here is to put everything in on the top. So I go 15 times 0.3 times 3. And if you're really good with your parentheses, you can put parentheses there and then divide by. So I hit enter and I'm dividing by 1,000 times 2. 1,000 times 2. And I get 0.00675 moles of BaSO4. BaSO4. Cool. So what I asked originally was what is the concentration of BaSO4. So let's just do that in one step. Notice I'm not going to just divide this over here. That's called magic math. If I just take this and divide my volume, what I'm saying is that this quantity here completely equals this quantity here. Instead, I'm doing a whole new step, so I need to not do that. It's not mathematically correct. Sorry. Hits my physics buttons. All right. So 0.00675 moles of BaSO4. And those moles, well, they were in, and in is going to go on the bottom, 30 milliliters of BaSO4. So 30 milliliters of BaSO4. And I might be tempted to feel like I'm done, but I'm not, because molarity is in terms of liters. So I need to finish that. So that's going to be 1,000 milliliters on the top per 1 liter of solution. And I put that in, and what did I get? I got a number 0.225. So 0.225 molar. Cool. Of BaSO4. So the other promise I made is that we can relate this to this and then come back and move these things up top, kind of ish out of the way, and start over. So I'm going to rewrite our equation that I have 2AlOH3 plus 3BaSO4, and that's going to go to Al2 SO4 3 plus 3BaOH2 BaOH2. Cool. And let's see what information that we have. We'll repeat that. I want orange. I said we have 15 milliliters of this and 0.30 molar. And we're going to now relate this, oh, and 30 mils of this. That's what I said, right? Yep. And 30 milliliters of this. So let's relate it to our product. So same process. I have 15 milliliters of AlOH3 times 0.30 moles of AlOH3 per 1,000 milliliters times, let's see, times my mole to mole ratio. I have 2 moles of my aluminum hydroxide to 3 moles of my barium hydroxide. So again, checking my units. That cancels. Whoa, not the 1,000. That cancels. And let's go with, I want moles of aluminum on the bottom to cancel out. So I have 2 moles of AlOH3 to 3 moles, that's the coefficient, 3 moles of BaOH2. Put that in my calculator, and I get that I have 0.00675 moles. It gives me 0.00675 moles of BaOH2. Cool. So to know what its molarity is, and hopefully you looked at this and you're like, well, this ratio for the aluminum to the barium is the same as it is for this ratio to the product, so it kind of makes sense that those two are the same. And I'm coming up with the same answer, which is true. But it will work regardless, so long as you're balanced and working through your coefficients correctly. This process will work regardless of if it doesn't look as pretty as this. So for my molarity of BaOH2, I have 0.00675 moles of BaOH2. And that is going to be in this total volume of solution. So this one will be in 45 milliliters of solution times my 1,000 milliliters per liter. And that gives me something, 0.15 molar. 0.15 molar BaOH2. Cool. So we have related our products to each other, our reactants to each other. We've related our reactants to one of the reactants to the product. And I could turn around and do the same thing here with my mole-to-mole ratio, going from my moles of BaOH2 to figure out how many moles of BaSO4 I have, and then put that in that 30 milliliters of volume to figure out its molarity. There's all sorts of ways that I could do that. Challenge yourself. What is the molarity of this Al2SO43, the aluminum sulfate? That's a fun one to know. In fact, next we're going to look at that, and then we're going to start looking at our ionic solution and molar concentrations of each of these things. So we have 3 of the 4. We can figure out this one next, and then we'll look at how many ions we actually have in the solution. All right, that's next.